Okay, I come from the future near the exam. Okay, and I would like to say that the plant capacity, right, in this system that you are actually looking at right now, that you watch this video already, I would suggest you watch this video, okay, for the plant capacity system. Alright, and we actually say that if the controller is very big, alright, if the controller is, because you think about it, your T naught is based on your U times your P naught, your plant, alright. So in other words, you would have a, for example, so your sensitivity, your control, your C over 1 by Cp, alright, is over here, your U, okay. So this is your control sensitivity function. So if you were to have a very large control, meaning you have a never mind, you link later in the near end video, you will know that U is equals to minus kx. Okay, it's for the state space, if you remember. Okay, for the feedback lah. Alright, it goes all the way back to part on A minus bk and doing the U minus. But anyway, in this case, you just know that your controller is in terms of some k constant. Alright, so if your controller is very large, for example, okay, in this case, this is the equation that we were doing. So if C is very large, so it's C over 1 over here. So if you have a very large C, you approximately become C over Cp naught. Alright, so you can try it out. You have about 1000, for example, if C is equal to 1000, and so you have 1000, if P naught is 1, for example, okay, so 1000 divided by 1000, alright, you have this C is equal to this C, right? I think you get what I mean. So in other words, you just need to know that if C is very large, you can try it out in terms of a math. Because I didn't bring my pen over here, so I can't write properly. But anyway, so if you have a very large C, your C is approximately your whole function over here is approximately C over Cp naught. So you can cancel. You'll have 1 over P naught. Okay, and therefore if you multiply by your plant, over here you have equals to 1. So your T, it will be equals to 1, which is not good, right? Because our plant capacity is somewhat 0.7 or 0.8 by standard. Alright, not by standard, but rather than typically the plant capacity where the plant is able to do work. Or if you exceed the plant, this means the plant is going to be unstable. So make sure your T has to be smaller than 1. I mean, some smaller than whatever the plant capacity is. Okay. So therefore, the gain itself, you can only control it to a certain extent. You cannot fully control it to a maximum that it is approximately 1 over P naught. Alright, so you want to control it to a certain extent that once, for example, the ratio over here should be approximately 0.6 or whatever. So you need to control your controller such that the output over here is somewhat 0.6. And then if you have to multiply by your P naught, you have, it's not 0.6, give me a while. In any other case, because I'm a bit rushing already, so therefore you just need to know that if you run your controller too big, it's good because you have 1 over P naught. Alright, when you multiply by P naught, you'll get equals to 1. Okay, it is good to a certain extent because if you do this method, alright, your reference signal, if you think about it, reference signal is over here, alright, you have an output over here. Your controller itself is somewhat changing it to 1 over P naught. So your purpose, or if you have a large controller, you actually whatever your response signal it is will become your output. So you have designed a good controller, but because of the plant capacity, there is a problem. So normally your C has to be controlled to a certain extent, such that your T has to be approximately 0.7. Okay, so therefore you want to choose the correct gain, which is approximately high but not too high, such that your T is equals to 1. Alright, so you have to choose the correct value of your controller such that your T is approximately 0.7 or 0.8 with regards to the plant capacity of your system lah. Okay, so this is something that you need to understand, although this presentation sucks, but at least the key concept over here is to know that the good thing is that if you run a high gain controller, it is good because approximately you have 1 over P naught times P naught, you get equals to 1. But however, although we want T equals to 1, which is the best, but because the plant itself cannot take it, so we want to design a controller slightly slightly less gain, such that you have a 0.7 or 0.8 ratio. Okay, so I hope that this is pretty clear, and that also need to know that if let's say if your controller is big enough, which is good, right, you will also have the possibility of reducing the steady state error. Alright, so this is something that you need to know, because if you run it to the in a high gain, alright, you can actually reduce the steady state error quite significantly well. So therefore, this means that you're going to have a reduction in the disturbance. Okay, and plant variation. So your plant variations may vary between time to time. I don't know what I'm talking, but you just need to know this lah. Because I come from the future, I made the exam, so this is the answer that is given. So I think it's fairly useful if you were to check it out now. Alright, so you just need to know that the controller that is big can actually reduce the steady state error. So steady state error implies that your signal over here should decay up to this particular point. But however, if you have a large gain, however, sometimes you may actually have a output that is something like this. So your desired is over here, this line, but however, your output is something like this. So there will be a steady state error, because this thing is steady state, this is steady state. So the error between the responses that you give and the one that you want is an error. So there is a steady state error over here. So if you have a high gain, or you can actually somewhat reduce the steady state error, alright, such that you can reduce the disturbance. Because think about it, if you have a high t, because s plus t is equals to 1, alright, so if t is 0.7 for example, then your s is 0.3. So you go back to last time the SDS. Remember, this is the equation for your output, right? So if you have a t that is pretty large, alright, 0.7, you have a big response and a big noise, and then you can use the noise filter to remove the noise, so that your output will be good. And then over here, your 0.3, you actually diminish your disturbance over here. You see, your disturbance is lesser and lesser. So this is why the larger your controller is, your t will be large, and as your t is large, your s will be removed. Alright, will be getting small and small. So therefore, you reduce the steady state error, and also to reduce the disturbance, and moreover the plant variations to a certain extent. Alright, because the plant itself may have a variations between, because let's say you have a model of machine A and machine B, they come from the same manufacturer, but they have some variations in between their parts or whatever, things like that lah. So for the high gain, it is somewhat, possible to do this and things like that. And yeah, another plant variations meaning is that perhaps if a long time your machines is running, it may actually have wear and tear. So wear and tear will actually cause your machine to have a certain variations from its original one. Or if you think about it, I don't know whether is it here we are. And also I think you have cleared away the Doyle stability criterion, because I think we are somewhere over here. Alright, l3v4, stability and operating frequency concept of the control sensitivity due to your plant capacity. So currently we are somewhere here, right? l3v3, l3v4. So previously we talked about the Doyle stability criterion. If you haven't watched, you watch. Alright, you get to know that your loop, at first your initial plant is something like this, and a long time you may actually change the Nyquist loop to slightly bigger, the loop gain, because of plant variations and things like that. So these are the things that you may want to know also lah. And this purpose of this video is to create all this link, which I see that is pretty useful in the future, I think. So I'll put it here. Yeah, see ya.